Hello everyone, my name is Cho-Ping Xu, and today I'll present our work, RoLGaL, Robust Learning for CVR Prediction via Guardrail-guided Labeling. This work was done together with Xiaoli Gao, Amir Roshankar, and Rong Jin. Our focus is a practical problem in large-scale advertising systems, how to continually update conversion rate prediction models using fresh data, while preventing noisy recent labels from damaging knowledge that the model has already learned. Let me begin with the main message. Production CVR models are frequently retrained, often every day, to respond to new users, advertisers, and changing market conditions. However, conversion labels are not always reliable. Noise in recent labels can cause the model to overwrite stable historical patterns, which leads to catastrophic forgetting. Our solution is RoLGaL. It uses guardrail-guided corrected labels to make the shared representation more robust. Importantly, we do not replace the training target of the primary serving head. The primary head continues to learn from the original labels, which helps preserve calibration. The corrected labels are used only by an auxiliary training branch. This branch improves the shared representation during training and is removed at inference time, so there is no additional serving latency. On Criteo, RoLGaL improves AUC by 0.25%. Under injected noisy labels, the improvement reaches 0.31%. In production, we observed a statistically significant 0.23% lift in a primary revenue-related business metric, and the method has been deployed to more than 10 production models. So the central takeaway is that RoLGaL improves robustness without changing the serving path or adding inference cost. Let's look more closely at the problem. Daily model refresh is necessary because the environment is constantly changing. We have new users, new advertisements, new products, and shifts in market behavior. But the new training data can contain noisy conversion labels. For example, attribution may be delayed. User actions may be accidental. Conversions may happen across devices, or logging systems may introduce artifacts. With naive continual retraining, gradients from the newest data can dominate the update. When these recent labels are incorrect, the model may overwrite useful patterns learned from much larger amounts of historical data. This is the form of catastrophic forgetting that we address. At the same time, a production solution must satisfy two important constraints. First, it should minimize changes to calibration. CVR predictions are used directly in auction bidding, so replacing the serving labels with aggressively corrected targets may shift the predicted probability distribution. Second, the solution should not add latency. Even a useful robustness mechanism may be impractical if it slows down real-time ranking. This leads to our main question. Can we make continual training more robust without changing the serving prediction itself? This slide shows the overall design. At the top, we use a shared encoder with two prediction heads. The first is the primary head. It is trained using the original observed labels, and this is the output used during serving. The second is the RoLGaL auxiliary head. It is trained using adjusted labels and exists only during training. Because the two tasks share the same encoder, the auxiliary task can improve the representation used by the primary task. The bottom of the slide shows how we construct the adjusted labels. We start with the observed labels from the recent training stream. First, we perform label recovery. Instead of treating each binary label as perfectly reliable, we recover a soft target that reflects uncertainty. Next, we compare that recovered target with a guardrail signal. The guardrail represents a more stable historical reference, such as predictions from the previous model checkpoint. Based on this comparison, we determine whether the proposed update is safe or risky. We then generate an adjusted label, which supervises the auxiliary task. The key architectural choice is separation between training and serving. Robustness is introduced through the shared representation, but the serving head and serving graph remain. Now I'll explain how the adjusted label is generated. The first step is label recovery. The basic idea is that the observed binary label may be a noisy version of the user's underlying conversion intent. We therefore use a lightweight, one-step probabilistic model to recover a soft target. The equation at the top computes the posterior probability that the underlying intent is positive, given the observed label. It combines three pieces of information: the observed label, a prior conversion probability, and an assumed noise variance. The important point is not the detailed form of the equation. The important point is that a hard 0 or 1 is converted into a softer, uncertainty-aware target. For example, instead of treating a positive label as definitely 1, the recovered target might be 0.8 if the observation is uncertain. The second step is guardrail-guided judgment. We compare the recovered label, Y star, with a guardrail label, YG. In our continual training setup, this guardrail can come from the previous stable checkpoint. If the distance between these two values exceeds a threshold, we mark the sample as risky. Otherwise, the sample is treated as safe. The final step is adaptive label adjustment. For a safe sample, we can use the recovered soft target. For a risky sample, we move the target toward the guardrail. The parameter C controls how strongly we trust the guardrail. In our standard hard gating configuration, the intuition is even simpler. For safe samples, use the recovered target. For risky samples, use the stable guardrail prediction. We also use multiple heads with different noise variances and risk thresholds. Each head represents a slightly different view of what should be considered noisy or risky. Combining these views reduces sensitivity to a single hyperparameter configuration. Again, these labels are used only for the auxiliary training task, not as direct replacements for the primary serving labels.
For our public benchmark evaluation, we use the Criteo Attribution dataset. It contains more than 16.5 million chronologically ordered interactions spanning 31 days. We use DCN-V2 as the common backbone for all methods. The timeline is divided into 3 stages. The first 14 days are used as a warm-up period to train an initial stable model. The next 7 days are used for additional training. For the final 10 days, we simulate continual learning. The model is updated on each daily batch and evaluated on the following day. To construct the guardrail without introducing future information, the previous frozen checkpoint makes predictions on the new daily batch before that batch is used for training. Those predictions become the guardrail labels for the current update. This setup reflects a realistic production pattern. Yesterday's stable model acts as a reference when processing today's potentially noisy labels. We first evaluate performance on the original Criteo training stream without additional label corruption. We compare RoLGaL with the baseline model, label smoothing, and knowledge distillation. Label smoothing provides almost no AUC improvement in this setting. Knowledge distillation is a strong baseline. It improves AUC by 0.22% and achieves the best point estimate for LogLoss. Single-head RoLGaL achieves a similar AUC improvement of 0.23%. Multi-head RoLGaL achieves the best AUC result with a 0.25% lift, while also reducing LogLoss by 0.55%. The main conclusion is that on relatively clean benchmark data, RoLGaL is competitive with strong teacher-based supervision. It does not sacrifice clean data performance in order to gain robustness. Next, we test the setting that directly motivates our method. We randomly flip a portion of the training labels while keeping the evaluation labels unchanged. At a 1% corruption rate, label smoothing slightly underperforms the noisy baseline. Knowledge distillation achieves a 0.19% AUC lift. Multi-head RoLGaL achieves a 0.31% lift, showing a larger benefit under corrupted supervision. We then increase the corruption rate from 1% to 5% and 10%. As the noise becomes more severe, the relative improvement from RoLGaL increases. The multi-head lift grows from 0.31% at 1% corruption to 0.43% at 10% corruption. This trend is important. RoLGaL's advantage becomes clearer as supervision becomes less reliable. The reason is that knowledge distillation broadly applies teacher supervision, while RoLGaL specifically identifies samples whose recovered labels conflict strongly with the temporal guardrail. The correction is therefore selective rather than uniform.
The ablation study helps us understand which components matter most. First, increasing the number of heads from 1 to 2 improves the AUC lift from 0.27% to 0.31% and reduces variance. Moving from 2 heads to 3 heads provides almost no additional improvement, so we use 2 heads as the default configuration. The most important result is in the module contribution section.
When we remove the guardrail, the lift drops substantially, from 0.31% to 0.12%. This confirms that selective guardrail-based adjustment is the key component. When we remove label recovery, the result decreases only slightly, from 0.31% to 0.29%. This suggests that the probabilistic recovery step provides complementary value, but the guardrail judgment is doing most of the work in this particular setup. In practice, this means that guardrail quality, together with the noise and risk thresholds, is especially important for successful deployment. Finally, we validated RoLGaL in a large-scale production advertising system. The development process began with auxiliary task integration and offline validation. We then conducted a standalone online A/B test. Over a 12-day test window, RoLGaL achieved a statistically significant 0.23% lift in a primary revenue-related business metric. After this initial validation, the framework was included in broader bundled experiments and rollouts. It has now been launched across more than 10 production CVR and CTR models. A major practical advantage is that this impact comes with zero inference latency overhead. RoLGaL changes how the model is trained, but it does not add a new model component to the real-time serving path. That makes the method relatively easy to integrate into mature ranking systems with strict latency constraints. To conclude, I would like to leave you with 3 takeaways. First, robust training. RoLGaL improves continual CVR training when recent labels are noisy and helps prevent unstable updates from overwriting useful historical knowledge. Second, calibration preservation. The primary head continues training on the original observed labels, while robustness is introduced through an auxiliary objective. This minimizes disruption to the existing serving distribution. Third, efficiency. The auxiliary branch is removed at inference time, so RoLGaL delivers online gains with zero additional serving latency. Overall, RoLGaL provides a practical way to use corrected supervision during training while keeping the production serving path unchanged. Thank you for listening. I'm happy to take questions.